Hi, so hopefully everyone can see my screen and hear me okay.
Yes.
So my name's Jess Hillman and I'm down here in New Zealand at GNS Science. And today I'm going to talk a little bit about some of the work we've been doing on gas hydrates around New Zealand. So kind of quick crash course in case anyone doesn't know what hydrates are. They're essentially a solid ice-like form of water, where you have water molecules in a cage. In that cage, you're holding gas molecules. These are predominantly methane, but they can also be higher order hydrocarbons as well. And because they obviously contain methane, natural gas, you can set fire to them. So fiery ice is another name for these. They're found in marine sediments and permafrost. So obviously we're looking at marine sediments around New Zealand, but you do get them in permafrost on land as well. So the main way that we can find these is using seismic data. That's because predominantly where you find hydrates, they create a seal because they act like a cement or kind of like a glue to hold sediment together. That traps free gas underneath. Obviously, you have to have free gas somewhere to be able to form hydrates in the first place. And that free gas being trapped there creates a really nice density contrast that shows up really well in seismic data as a BSR. And the reason for that is that the bottom simulating reflection is that they are stable at certain pressure and temperature conditions, and so that basically means they follow the trace of the seafloor. So moving to New Zealand, we've done quite a lot of work around New Zealand looking at seismic data to try and identify where we find these hydrates, and they've been identified in quite a few places. So offshore Tasman, see there's some indications of BSRs. There's an example here in the seismic line. There's also some indications of Pusica and Fiordland off the South Island to Waipounamu. On the Chatham Rise, we've been doing some work under a different project, which I'm part of, which is potentially looking at there actually being CO2 hydrates. So a little bit different to the more conventional methane hydrates. But today I'm going to focus on the Hikurangi Margin, which is offshore Te Maui or North Island. And here we definitely know these are predominantly methane hydrates. They're about 99% methane. So the Hikurangi Margin is New Zealand's largest gas hydrate province. It covers an area of about 50,000 square kilometres. You can see on the map here all those red dots show you where we've identified BSRs from the seismic data. We've also got a lot of indications for active gas seepage, and we can see other indications such as pockmarks of potentially past seepage as well. And that was studied by Sally Watson, which came out in 2019. So the Hikurangi Margin is a very, very large subduction zone where the Australian plate meets the Pacific plate, and as the Australian plate is being kind of smushed against the Pacific plate, that creates a lot of deformation, and the overriding sediments get forced up into accretionary ridges. And there's a very strong connection in this area with the deformation of these sediments and where we see hydrate accumulation occurring. So in the last few years, under a program that I lead at GNS Science, we've had a really intensive data acquisition program in the southern Hikurangi Margin, so quite near to Wellington, where I'm based. And here we've been acquiring high-resolution 2D seismic data. So that's the black lines you can see on the map. And this has been basically, we've gone back to areas where we saw those indications for highly concentrated hydrate from existing seismic. So we've gone back and collected more focused data over those locations. We've also more recently added controlled source electromagnetic data in collaboration with Scripps. So that's the yellow lines you can see there. And we've also had some targeted biological surveys using both towed camera systems, sediment sampling, and a couple of ROV dives, which we're very lucky to get through collaboration with some US partners using ROV Jason and ROV Ropos. And this has actually allowed us to redefine the southern extent of the hydrate province offshore Kaikoura. So right down in the southern extent of those lines, you can see there are a few patches of small patches of BSRs down there, and really extensive gas seepage at one of the sites where we've done an ROV dive actually earlier this year. So this gives an example of some of that high resolution 2D seismic data that we've been collecting. And you can see here you've got hydrate occurring within the apex of these anticlinal ridges. And these have essentially formed as a result of large thrust faults that soil out towards the deformation front. And that forces up these ridges, and they then become essentially a kind of structural trap. And we have a combination of factors acting here. So both the thrust faults bringing up deep source thermogenic gas, and then also shallower biogenic gas being created by microbial action within the sediments. And so there's a few different factors here. So both tectonics and the sedimentation patterns really control where we see these focused, concentrated gas hydrate accumulations. So we very rarely see hydrate forming in the interstitial basins, and there's a definitive pattern of it occurring along these ridges. And we actually do see it outcropping at the seafloor as well. So that image just shows an example from the larger ridge here, which is called Glendew Ridge. So some of our colleagues here at GNS have actually been working on whether we can test out this hypothesis that there's these different factors of the structural and the sedimentary kind of controlling the formation of the hydrate. And so we've been doing this using 3D modeling in Petramod, and that's been led by Carsten Kroger. So we had a paper out just recently on this. And this does demonstrate that we have these spatially variable rates of microbial gas generation within the shallower sediments. We also have significant gas recycling at the base of the hydrate stability field. But there is a significant factor still of gas migration coming up through these deeper faults, which then feeds into the deformed sediments within the ridges, and that kind of channels the flow essentially right into the apex of those ridges, creating that really concentrated, focused hydrate accumulation. And that's the paper that's out recently. We've also been looking at the connection between these hydrate accumulations and where we see active seepage at the seafloor. And that's for a few different reasons. We're obviously interested in what the structural controls might be, but we're also looking at the biological aspect, which I'll talk a bit more about in a minute. So one of the studies we focused on was a small ridge that creates, again, a kind of structural trap. And we know that there's a clustered normal faulting in the upper sediments. And so we wanted to see whether those normal faults were acting as conduits for gas flow, or whether there was something else at play here. And interestingly, at this site, we actually found that it's not normal faults that the gas is flowing along, even though there are lots of them, they're not being utilized as flow zones. But what we showed instead was that there's this doming of gas right above an accumulation of hydrate. And the reason that's been able to form at this particular site is that we have mass transport deposits, which are stacked up through the sequence here. They're related to active deformation along the margin and these ridges being pushed up, and you have intermittent slope failure. And that mass transport deposit has slightly less permeable sediments contained in it, which actually creates a seal. So you can build up this accumulation of gas. Then eventually you reach overpressure, breakthrough occurs, and that's what's created this fluid flow conduit all the way to the surface. And we can still see gas seepage occurring at this location at modern day. And that was published just earlier this year by one of my colleagues, Gareth Crutchley at GMR. So this is just a little video of one of the sites we've been able to visit with one of the RVs. This is RV Ropos, and this just shows that these seeps are, they are really active in places, and they're obviously links to significant development of orthogenic carbonates, creating valuable hard ground habitats for organisms. And they're also known to be, these accretionary ridges and the seep sites are known to be focuses for trawling activity in fisheries, because they attract fish and provide ecosystem services. So this is one of the sites that's been trawled quite heavily. You can see there's not a whole lot of life around the seep. There's a few kind of unhappy looking tube worms down the bottom of the image there. So if we go to one of the, if we go to one of the seep sites that hasn't been trawled, this is at a much deeper site. This is over 2,000 meters down. You can see the kind of life and the abundance that we do see in these locations. So really, really abundant tube worms, mussels, clams, other chemoautotrophs here. So these seep sites are supporting really significant ecological hotspots. They support really unique seep fauna. And these take thousands of years to establish. They don't recover quickly, so they're very vulnerable to damage from things like trawling. And the reason we were looking at this was particularly thinking about, do the hydrates play a role in slope stability here? And also what would be the potential impacts if we ever were to go ahead and produce hydrates for an energy resource? That's something that's very unlikely to happen in New Zealand, but we now have a really good understanding of what the potential implications could be. So we've been trying to basically document these sites and think about the shallower sites that have already been damaged. What are the implications of that? And moving forward, do we need to do more to protect these valuable ecosystem sites where they haven't yet been affected? So that was a very, very quick kind of crash course run through some of the work that we've been doing. And this is obviously work that's been done with a lot of people, both here in New Zealand and also internationally. So I just want to say thank you to all of our collaborators. And hopefully some of you found that interesting, and if you have any questions, I'd be happy to answer them at the end of the session. Thank you.